All right, welcome back to Calculus AB, everybody. Today's topic 4.4 Introduction to Related Rates, and topic 4.5 Solving Related Rate Problems. So, our next application of derivatives will focus on two or more rates that are simultaneously changing. So, we call these types of problems related rates problems. So, two or more things that are changing at the same time. So, first, let's begin conceptualizing how two rates can coexist. So suppose water is poured at a steady rate into containers whose shapes are shown. Sketch the graph of the height of the water versus the time for each. So if you guys notice on the first one right there, if I were to start pouring water in here, right? So it should like start filling up easily, right? So if you start pouring water, right, it's gonna keep adding water at a steady rate. So I would say this relationship happens to be linear, like so. All right. Now, on the next one, right? So this one, the bottom part, if you guys notice right here at the bottom, it's a lot thicker than pretty much. Well, it's wider than what we have on top right here. So what's going to happen is that this is going to start filling up a little bit slower, right? So it's going to start filling up slower. I would say it is still at a constant, steady rate, not a curve, right? So steady. And then once it starts filling up where it's more narrow, it's going to start to go a lot quicker. So it should be a little bit more like this. All right. And then if we look at the next shape, which looks like the letter I right there, pretty much. So again, I would say it would be like a combination of the first graph and the second graph, kind of, right? So in this case, we're going to start off slow, right? Filling in slow because it's wider at the bottom right there, and then it's going to go quick, right? So it's going to go quick, and then again, it's going to continue on the same, almost the same as it was before. All right. And then the last thing right here, the combination of these two cylinders. So we're looking at pretty much again. First, is it's going to start to fill out fast, right? Because again, that the bottom part is more narrow than the top part. So here, this starts to fill out fast, and then the other one goes at a slower rate, like so. So that should be pretty much. So again, those two things are what we're looking at: the height of the water, right, and the time, and then depending on the container, it's how it gets filled. Okay. So now let's look at the next thing. Says example two: write the following statements mathematically. So John is growing at a rate of 3 inches per year. So that means he's changing. So whenever you guys see the word rate, that means he's changing in some way, right? So keep that in mind, please. So let's say use that one. So we're gonna say that here the thing that is changing. It's his height over each year. So we can say dH dt, right? The rate at which he's changing is 3 inches per year. So now we're looking at part B. It says my mutual fund is shrinking by 4 cents a day. So it's still right. It's still changing your mutual fund. So the amount of money over time, right? So it's still going to be over time. And in this case, we're going to say D DM, right? D for money, and then equals pretty much 4 cents per day. All right. And then part C gives us the radius of a circle is increasing by 4 feet every hour. All right. So I would say here R would be like a good function to use, right? Because it's the radius. So dr dt equals 4 feet per hour. All right. It says the volume of a cone is decreasing. So part D, the volume of the cone is decreasing by 2 inches cubic inches per second. And I just noticed I made a mistake on part B. So if you guys notice, this is my mutual fund is shrinking by 4 cents. So shrinking meaning it's getting small, so that should be a negative rate. This one's positive because it's increasing, and then this one's growing. That's why it's also positive. So the volume of a cone is decreasing. So I would say dV over dt equals -2 cubic inches per second. Yeah, I almost missed that part, right? The word shrinking. So make sure you guys are always looking for those words as well, right? So decreasing, increasing, one's positive, the other one's negative, and so forth. All right. So let's look at Example 3 now. So in example 3, we have a rectangle. So it says a rectangle is undergoing changes in its length and width. A rectangle's length is increasing at a rate of 2 inches per second, and its width is increasing at a rate of 3 inches per second. Find how fast the perimeter is changing at the moment its length is 10 inches and its width is 10 inches. All right. So let's try to create a little picture just to give ourselves a little sense of what's going on, right? So it is a rectangle. So that's a pretty easy shape to draw, right? Let's draw ourselves a rectangle. And then here we have a length and a width, right? So length and a width. All right. And then we're given that the length changes. So dl dt is equal to that 2. So yeah, so 2 inches every second, right? So 2 inches per second. And then we're also given that the width, dw over dt, is changing at a rate, is increasing as well. So at a rate at 3 inches per second. All right. So that's another given. And then what we need to find, they're asking us how fast is the perimeter changing? So we need to find dp over dt. All right. So we need to find pretty much the equation, and we know it's given by p equals 2w plus 2l. All right. And so from here, pretty much all we have to do is take the derivative implicitly. So when we take the derivative implicitly, just remember you're taking in this case, you're taking the derivative with respect to time. So we would say dp over dt equals, right? And that's pretty much what we need to find. 2 times the derivative of w would be dw over dt. And then the derivative of L would be plus 2 times dl over dt. All right. And when you guys simplify this, pretty much you're plugging in just the values that you have here that you guys were given. And in this case, it happens to be 2 times 2 plus 2 times 3. So that's equal to 4 plus 6 gives us 10. So we can say that pretty much this is changing at a rate of, yeah, so we can say the perimeter is changing at a rate perimeter is changing at a rate of 10 inches per second at t equals, oh no, at that moment, right, when this was 10 and then this was 6. All right, so no t. So it's just at that moment, pretty much, when it was, the length was 10 and the width was 6. It happens to be 10 inches per second. All right, and then part B, we're looking at now the rectangle's length is increasing by 3 inches per second and its width is decreasing by 2 inches per second. So find how fast the area is changing. At the moment, its length is 10 inches and its width is 6 inches. Now, if you guys notice, mainly I'm just using these numbers right here, right, which is how it's changing, right? And this one, we might need it at some moment, but since we're taking the derivative of w, all we get is just dw over dt. So if it was like w squared, then probably these values would be involved, all right? So we do have to be careful. So here we're given, again, it says the length, so we know dl over dt is equal to 3 inches per second. That's increasing, meaning it's going up. And then the second one, which is dw over dt is equal to negative 2 inches per second, all right? And then again, it says find how fast the area is changing. At the moment, its length is 10 inches. So we know that the area, right, we're looking for dA over dt. So the area for any given rectangle is length times width, right? So from here, we want to make sure that we pretty much just set it up. We find the derivative. Now be careful here because you do have to use the product rule. So set up your fish, right? So this would be dl over dt. And then this would be dw over dt. Draw your fish, and there you go. That's dA dt. We plug it in, so that would be L times dw over dt, and then plus W over DL over DT. So if you guys notice here, then yes, I would need these two values right here, right? The 10 and the 6 pretty much, all right? So I do have to make that substitution. Okay, so let's make that substitution. Let me finish it off over here. Oh, that was a picture. It's still the same picture, right? And then, so let me do a different color here. Okay, so we would say dA over dt equals pretty much L, which is 10, times dW, which is -2, dW over dt, and then plus you have width, which is 6 at this moment, and then dl over dt happens to be +3. So here we have -20 plus 18 equals -2. So the area is changing, right? Or is decreasing, I would say better, instead of changing, just decreasing. Sounds a lot better. So is decreasing at a rate of 2, in this case would be square inches, right, per second. Is that the correct units? Yeah, it would be the correct units. Because here you have inches, right? Here you have inches over seconds. So inches times inches, you guys get inches squared over seconds, which again is pretty much how you find the area is always squared, right? And that would be pretty much it.